So, I cannot share my screen here for some reason. Don't know what's happening. Okay, hopefully things are now all right. So you can all see and check, right? Everything.
Yes, sir. Yes, sir.
So you can all see and hear.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. Hopefully things will not fall apart again. Let me move over these things. Uh, Let me check if I'm recording. Yes, I'm recording. So then, as I said, the definition for this probability is that probability uh, to observe uh, x in the interval uh, x to x plus dx should be given by fx times dx. So remember, only fx doesn't have a meaning, but only fx times dx gives you the probability. Okay, so you always need to specify an interval of x in which you want to observe x. Okay, and this fx dx will give you that probability. So of course, since my total probability should be 1, so if you integrate fx dx, that should be equal to 1. Okay, so that is the normalization of the distribution function, and then this fx will be called the probability distribution function. All right. Now there is another important thing that I need to specify. Is called the cumulative distribution. So, cumulative distribution function. So this is defined as if x is the random variable, then fx uh, will be the cumulative distribution is the uh, sorry is the probability that the random variable will have value less than equals to x. So that is the cumulative distribution for the random variable x. So in terms of the probability distribution, fx is equals to say minus infinity to x. So if the x ranges from minus infinity to plus infinity, then fx is basically from minus infinity to x, say fx prime dx prime. That is the total probability that uh, x prime will take, or the random variable will take values that is less than equals to x. Okay. Now, if you notice carefully, then you can define the probability distribution as a derivative of the cumulative distribution function. How do you do that? So if you try to find the cumulative distribution function, so say if x plus dx, the cumulative distribution function of x plus dx, that it will take the random variable will take values up to x plus dx, then that will be given by minus infinity to plus x plus dx fx prime dx prime. Okay, so quite evidently, if you take f of x plus dx minus fx, then that should be, if you change the limit, so x to x plus dx fx prime dx prime. And if this dx is really small, this dx is tending to 0, then you can approximate this as this is fx times dx, because it will stay at a constant value fx, and you multiply by that dx. So the fx, the probability distribution basically becomes f of x plus dx minus f of x divided by dx in the limit when dx tends to 0, and that is the formula for the derivative of capital F. So the probability distribution is obtained as the first order derivative of the cumulative distribution function, and sometimes the cumulative distribution is important in that regard. Okay, so good. Now, the next thing I will discuss is the some other properties that we can find using this probability distribution function. So we will now proceed to define something called the expectation values. Okay, so the expectation values of anything, any function, is the kind of the average value of that thing, and this is defined quite simply as, suppose you want to find the expectation value of x. Okay, so suppose you want to find out the expectation value of x, then that will be given by integration over the range of this x times fx dx, and so this is called the expectation value of x. And people who are already familiar with quantum mechanics, they already know what I am talking about. So the average value of x will be given by the probability to find x in that region times that thing that you want to average over. You multiply by that corresponding probability, multiply that value by the corresponding probability, add over all the possibilities, and you get your average value. Okay, so that's how we define our averages in general. So in particular, the expectation value of x is the average of x, and usually we reserve the Greek symbol mu for to denote the average of the expectation value. But in general, what I'm talking about, this suppose expectation value of anything, suppose expectation value of a function of x, say gx, that will be given by, say, g of x times f of x dx. Okay. That is the general definition of the expectation value. Some of the expectation values are more interesting than the others. So this first of all, let us define something called the moments. So this is alpha n. It's called the nth moment. Okay, so that is defined as the expectation value of x to the power n. Okay, and of course the definition is integration of x to the power n fx dx. And but this is not very useful if you just calculate the moment. This is only useful if your expectation value of x is 0. But more often than not, you will be interested in determining whether your distribution is symmetric or not. And when you talk about the symmetry of a distribution, you usually talk about, is it symmetric about the mean? Okay, is it symmetric about the mean value of the distribution? So you do not want to basically you want to nullify the effect of the shift of origin if there is one in the distribution function. Okay, so you want to choose the origin at the mean value, at the means x equals to mu, and then you want to kind of check the symmetry or asymmetry of the distribution with respect to that mean position. Okay, so whether the distribution is symmetric or not. Now that's why it is often useful to define something called the central moments, which I will denote by Mn. This is the nth central moment. Okay, and that is basically the expectation value of x minus mu uh, whole to the power n. Okay, and of course that is given by uh, x minus mu to the power n fx dx. So by doing this, what you are doing is basically you are shifting the origin from x equals to 0 to x equals to mu. Okay, and you want to judge the feature of the distribution with respect to the mu. So the central moment for n equals to 2, so the m2, which is the second central moment, uh, so this is very important in judging the quality of measurements that I will talk about in a moment. So this is usually called the variance. So the variance, which I usually denote by v of x, and it is sometimes also denoted as sigma square, and this is equivalent to m2, that is basically integration of x minus mu whole square uh, times dx. Okay, so now this variance is the expectation value of x minus mu square. Okay, so so let me write it down. So this is expectation value of x minus mu whole square. So remember that I will sometimes write it interchangeably as say expectation value of x square minus mu square. That is kind of let me put it this way. That is kind of expectation value of x whole square. This is simply because you can expand this x minus mu square into its binomial expansion form. So x square minus 2x mu plus mu square. Okay, and then the expectation value by definition is just this integration. So if you expand, you are basically taking the expectation value of individual things, right? So this whole thing basically becomes so this is basically expectation value of x square minus this mu is a constant, so you say 2 mu times expectation value of x plus mu square, okay, because the expectation value of 1 is already 1. Now this expectation value of x is nothing but mu again, so this is minus 2 mu square plus mu square. That's why I usually write this is expectation value of x square minus mu square. So whenever I find this is more convenient to write for variance, I will write this, and sometimes I will write this interchangeably, and they mean the same thing, just to make things clear. And another thing is that what does this variance tell you about the distribution? It tells you how spread your distribution is. Okay, so suppose if I give you say two distributions, so Uh, People who are already trained in statistics probably knows all these things, but people who are seeing this for the first time uh, might not be. So suppose I have a distribution uh, like this, and another distribution. Uh, I'm not drawing it very well. So you get the idea. So this variance gives you kind of the width of the distribution. So this will have the blue curve will have the smaller variance. So this is called, it will have the smaller variance. Okay. And the orange will have a larger variance. Why is that? So notice that the what is the definition of variance is sum of all of x minus u mu whole square. So remember what happens in an actual measurement. So in an actual measurement, what you do, you just uh, you just measure a quantity. Okay. So suppose you are measuring different values of say xi. Okay. And so you have listed x1, x2, x3, x4, and suppose you had measured, say this is 1.39, this is say 1.62, now 1.53, and you have measured many things, and all these measurements have given you an average value mu, that is basically sum of all the measurements over n. Usually you define the mean in that way. There is nothing wrong in that. That is, you are putting equal weight to everything. Anyway, suppose you have this, you have calculated the mu in this way, and now if you compute the variance, so the variance is something like basically sum over x minus mu whole square, uh, the average of this basically. So if I put equal weight, it is divided by n naively. Okay, and so yes. So xi minus mu whole square. And notice that this square is always positive, unless all these measurements, since you are never very close to mu, all these measurements actually, when you add these things, they add up to give you a finite variance. Okay, so the more scattered these values are, uh, if the values are all over the places, then you will have then we'll have a lot of spread around this mu, and this square will sense the difference only. It doesn't sense whether you are below mu or you are above mu. It only senses the difference. So that square will reflect the error, the randomness you have in your measurement. But in the ideal scenario, in a say a very good experiment, all these xi that you measure, all these x's are very close to mu. Let's say exactly equal to mu, and you have a, suppose that the ideal experiment you have, and you measure everything that is equal to mu. Everything is say 1.39, 1.39, 1.39. Everything is the same value. Then this difference is zero for each case, and your variance will be zero. So for the variance to be zero, the ideal distribution for which the variance to be zero is the delta function. And in practice, you never have the delta function. So and if you usually have a finite variance, that variance basically tells you how spread your measurements are, and it kind of reflects the statistical error in your measurement. So usually when we quote the variance, this sigma square, we actually quote the statistical error in my measurements. This is a recurring theme in our lectures, so you will see this uh, time and again in the course of the lectures. Okay, so this is kind of what variance means or sigma square means. By the way, it is sometimes denoted by this sigma square. Notice that if x is dimensionful, then sorry, I forgot an fx here. So if this x is dimensionful, then v of x has the dimension of x square. Okay? So v of x has the dimension of x square, and so the sigma has the same dimension as x. Okay, so that's why we denote it by sigma square, because if we need to keep track of the dimension of x, then we know that sigma carries the same dimension, and if we need to make something dimensionless, we just divide the quantity by an equal power of sigma. And that's the standard way of doing so. Okay, so first thing, to then to the first example you will find of that is when you define something called the skewness and kurtosis. So first of all, let me define the skewness. The skewness is defined in terms of the third central moment. This will not be very important in our lectures, but anyway, you should know what this means. So M3 by sigma cube. This is the definition of my skewness, and there is this called kurtosis, that is denoted by the symbol gamma 2, and that is de defined by M4 by sigma 4 minus 3. First of all, note that both these two are, as I defined it, are dimensionless, because mn has the dimension of x to the power n, and I am dividing it by the equivalent power of x. So these to make it dimensionless. Now, what does these quantity give you? What is there? What do they suggest? So this one suggests how skewed your distribution is. So this tells you how skewed uh, your distribution is. So that so quite evidently for a symmetric distribution, skewness is 0. So skewness equals 0 for symmetric distribution. Okay, and for distributions that are weighted heavily towards the larger values of x, that means it shows a bias towards x greater than mu, will have a positive skewness, and the distribution which is inclined more towards the lower values of x will have a negative skewness, because skewness is proportional to m3, and m3 is proportional to x minus mu whole cube. So depending on whether you are on x greater than mu side or x less than mu side, it can change the sign. Okay, so that is what skewness gives you. And the kurtosis, this is a bit more involved. It tells you whether your distribution uh, dies off faster uh, at extreme uh, x values compared to an equivalent Gaussian distribution. Okay, so what I mean by that is that ideally your distribution should extend up to plus minus infinity, right? So if you take a Gaussian distribution, so the Gaussian distribution is kind of this bell-shaped curve. If I draw it, like this, so this is kind of my bell-shaped curve that is uh, forming that. And this kurtosis tells you whether, if you have another distribution, suppose the distribution kind of looks like, um, say it looks like this. So by extreme x values, I mean the values of x like around here, near infinity, near x tends to minus infinity plus infinity. You look at the tail of the distribution, and you judge, like in on any side, you judge whether the distribution is falling towards zero faster or slower than equivalent Gaussian distribution. Okay, so if this happens, like if it drops off slower, I guess then it will have a positive kurtosis, and if it drops off faster than equivalent Gaussian distribution, it will have a negative kurtosis. Okay, and the idea, so why this 3 is included here? So this 3 sounds strange. So this 3 is included here to by definition. So by definition, we make so we make gamma gamma 2 equals 0 for a Gaussian distribution, and that's why the 3 is there. Okay, so by definition, the kurtosis of a Gaussian distribution should be 0 because we are comparing everything with the Gaussian distribution. So that's why the 3 is there in the definition. Okay, so these are some standard definition of quantities that might be of importance in future, especially the mean and variance. So remember the mean and variance very well, and we will come again and again to those definitions. Okay. So then there is another thing that I need to define, that is called the covariance. Okay. So before I define covariance, I need to generalize the idea of this probability distribution in case there are more than one variable. Suppose my distribution has two variables, say f, x, y. Okay, and then what do I mean by that? Then what I mean by that is that if you so this kind of distribution means that if you have two random variables x and y, the probability for x belonging to x plus dx and y to y plus dy. So remember, these are simultaneous, so they will be simultaneously inside each other. Okay, I mean, so x will be between x plus dx and y will be between y plus dy. The probability for that, by definition, will be fxy dx dy. So this is kind of the two-dimensional generalization of the probability distribution. So whenever we have this kind of more than one random variable, we can define something called a covariance. So the covariance will be between two variables, x1 and x2. So let me say x and y for brevity now. Suppose I have two variables. So covariance between x and y will be given by expectation value of xy minus expectation value of x dot expectation value of y. Okay, so that is kind of the definition of a covariance. Now the thing is that why we call it a covariance, it will be very apparent. Suppose if my f xy, if my x and y are independent of each other, then what I can do is that, so let me notice, so if x and y are independent, okay, then the probabilities for them to be on each block will not depend on the other. What I mean by that is that whether x is within x to x plus dx will not affect whether y is within y plus dy, uh, y to y plus dy. So you can calculate each of the probabilities independently. Suppose this probability I call say fx, say f1x dx, and this probability will be denoted by f2 y dy. So these are two independent probabilities now. So then for them to be simultaneously within the x to x plus dx and y to y plus dy will be basically f1x times f2x, sorry, f2 f2y dx dy, and then you identify this as your the combined distribution of x and y. So you see for x, and if x and y are independent, then your distribution is factorizable into individual random variable, individual distributions of random variable. If that happens, then if you calculate the expectation value of xy, okay, if you calculate the expectation value of xy, then uh, the that will be given by integration of say, let's say xy. So this is the thing that I am taking the expectation value times the fxy, the distribution function, dx dy. Now if this f xy is factorizable into individual parts, okay, then I can calculate the expectation values individually. So I can write say x f1x dx times y f2y dy. And if you recall, this is just the expectation value of x, okay, and this is just the expectation value of y if I integrate out the other parts, okay. And then this expectation value of x times y uh, breaks down into expectation of value of x and expectation value of y. So then in this case the covariance becomes 0, okay. So this kind of justifies the name covariance in the sense that if x and y are independent, then the covariance of x and y will be 0, and the distribution basically is factorizable. Remember, the opposite is might not be necessarily true. Okay, if your covariance happens to be 0, then it might not always imply that if x y is factorizable, that means x and y are independent. There can be a weird form of this weird functional form of this f x y, which can make this integration to be accidentally 0. So the essential idea is that if they are independent, your covariance is 0. But even if your covariance 0, you just you might not want to jump to the conclusion that your random variables are independent. There might be some other things, some other funny things going on inside, that for which we need to probably do further tests, further statistical tests. Okay. Now again, this covariance thing, this covariance has, if I take the dimension of x and y, so the dimension of a covariance will be the dimension of x times dimension of y, if my x and y are dimensionful variables. Uh, so this is so for this it is often very useful to work with a dimensionless quantity, which I called the rho, and rho is defined as the covariance of xy divided by the variances of many, basically the standard deviations of x and y. So so this kind of definition makes it dimensionless. First of all, that is, uh, it is always useful to work with dimensionless quantities so that you can base your conclusion, you can generalize your conclusion across different things, because it does not depend on the dimensions of the quantities that you are measuring. Okay, so it gets rid of that thing. And this dimensionless quantity is sometimes referred to as correlation. uh, so uh, so this row is called basically the correlation. Okay, and if you have this the another thing is that what does it mean that why what is does it mean by correlation and covariance? So this covariance can be positive or can be negative. Okay, so if you have covariance to be positive, then that usually implies that if x increases, y also increases. Okay, so an increase in x will also increase in y. It will be positively correlated. And if it is negative, then it usually implies that if one increases, then other decreases. Okay, so my suggestion is that you take a uh, sample distribution functions, like you take examples of this fxy from textbooks or whatever, where this sometimes you will see from the nature of this fxy plot that if they are uh, anti-correlated, then the correlation matrix will be negative, and if they are correlated, the correlation will be positive. So the last generalization is that if you have more than two random variables, say you have n random variables, then instead of just one correlation, you will have many correlations, and it is useful to talk about a correlation matrix. Okay, so first you define something called the covariance matrix. So Vij, the ijth element is given by, this is basically covariance of xi uh, and xj. Okay, and correspondingly you will have rho ij, which is given by Vij divided by sigma I sigma j. Okay. So, and we talk about this covariance matrix for more than, so I call it the covariance matrix. Okay. And you should note that for I equals j, say I equals basically covariance of xi and xi. So if you plug in the definition, it is expectation value of xi square minus expectation value of xi whole square. By definition, the difference of these two expectation value is the variance of the ith random variable. So I call it the sigma I squared. So by definition, VII is sigma I squared. So you see the covariance matrix is something whose diagonal elements are just the standard deviation in the corresponding random variable, and the correlation in the corresponding correlation matrix, uh, the diagonal elements are always 1. So rho ii is always 1. That means they are perfectly correlated, and of course, I mean xi and xi will be perfectly correlated. They are the same thing. So so that is kind of the end of the formal definitions of the quantities that we will need in these classes. I think I am kind of, yes, I have almost killed the time, and okay, let us end the class here, and then we will define other things in the next class, which is on Saturday. Okay, so remember, the next class is on Saturday from 2 to 3. Okay, uh, so now I will take questions if there are some questions.
Hello, sir. Hello. Hello.
I could not hear you, Soham, if you were saying something.
Sir, can you
Uh,
hear me?
you can write in the chat. I cannot hear actually. I don't know why. Maybe my audio is broken. Let me check. It- Yes, you have to write in the chat. I think I cannot hear anything. I cannot hear. I don't know why this is happening today. But please type in the chat your question. Can the class timing be changed? On Saturday, right? I mean, if instead of so 3 and 4 to from 3 to 4, I have meeting with my master student, and so then I can do from 4 to 5 if that is okay with everyone. So if you are asking about that, then I can do from 4 to 5. Okay, 4 to 5 is okay with everyone. Everyone type okay if that is okay with you. Okay, then I will see you from 4 to 5. This thing. Uh, I have just one questions to you. Uh, can it be done on 4 days weekly? So we have 4 classes per week. Yes. I don't think so. I have to maintain some schedule. Either otherwise, IIT. So this is IIT's rule. I mean, I cannot take 4 to 5 every day. Okay. So for Saturday it's okay, but otherwise I will screw up the schedule, and I don't want that. So let's say on Saturday from 4 to 5 only, and then as usual. Okay. So I just have one query. I see a student named Abhishek Meena. So have you registered for the course, Abhishek? I mean, I'm just wondering. I have no problem if you attend the course. I mean, I did not. I guess I missed your name in the uh, at all. If you are listening, can you tell me if you are registered for this course? And I mean, what are you expecting? All right.